All right. So welcome to what is probably your first honors physics video, right? So today we're going to learn about how to deal with objects that are moving at what we call a constant velocity, all right? All of my worksheets will start at the very beginning of the worksheet. I'll have a list of objectives. Sometimes I'll call them learning targets. It's actually what I should be calling them. And I'm in the process of adding those objectives, those learning targets, to the start of every video, okay? I will not, however, read through them all, because you guys can all read, right? So, but basically my recommendation is when you start each of these videos, you should pause when you get to the screen and take a second and read through these, because it'll tell you kind of what the things are that you need to look for as you watch the video, okay? So that is that, all right? So here's the deal. So in your math class, somewhere in your education, you've seen this equation before, right? Distance equals rate times time, okay? And so you learned how to apply it, and so, you know, maybe you have an example like this, where it says a car goes at 70 miles per hour. Oh, that's my rate, and it's doing that for 3 hours, that's my time. So the distance that I'm going to travel is rate times time. So I'm going 70 miles per hour. Notice I wrote that as a fraction. And I'm doing that for 3 hours. My hours cancel out, and you end up with 210 miles, right? So that's a thing that I'm guessing most of you have seen somewhere before in your education. So cool, right? 70 miles an hour, you do that for 3 hours, you're going to go a total of 210 miles. So everything here is fine, but we're sort of oversimplifying things, all right? So why is that so? Why are we oversimplifying? Well, so I guess the first issue is this. So most of us probably would refer to this particular rate as speed, right? Because it's telling you how far you go per unit time, right? Okay, so that's probably more commonly called speed, and maybe, in fact, maybe you learned this equation as distance equals speed times time, which is fine, okay? In order for this equation to work, in order for this equation to work, your speed has to be constant, right? You've got to always be going 70 miles an hour, right? If you sped up and you slowed down for some of the time, then this equation wouldn't make sense, right? Because you'd have a bunch of different rates. Unless, sometimes this will work if you're given an average speed, okay? So I could have, instead of saying a car goes at 70 miles per hour for 3 hours, I could have said a car averages 70 miles per hour for 3 hours, and then our equation would have been good again, okay? All right? Okay, and then the third thing that I guess I want to point out, I think this is the last one. So what you're finding there when you calculate that distance, what you're actually finding is the total length of the path that the car followed, all right? So maybe the car went east for an hour and a half and then west for an hour and a half, and so it started and ended at its starting point, okay? But the distance that the car traveled in this example is 210, whatever it was, miles, okay? So the distance that you find in that equation is the total length of the path that you followed, okay? Now, in physics, we're going to use a very similar equation, but it's not the same thing, all right? And I want to make sure that you guys understand the distinction between them, okay? So in order to get there, we first of all need to learn a new definition, all right? And so the definition we need to learn is what's called position, all right? Anytime I introduce a new variable, I'll try to put it in bold print like this, and then I'll give you the abbreviation for it in parentheses afterwards here, okay? So in this case, the symbol that we're going to use for position is the letter X, okay? And this just tells us an object's location on a number line, okay? So, drop my pen. So, for example, if, maybe Sally is standing right here. So here's Sally, hello, right? So I could write the position of Sally is -4 kilometers, okay? So it just tells your location on a number line, all right? And notice that, maybe she goes for a walk and she can move around, right? Okay? And so her position can change, okay? So in that instance, Sally had a starting position that was -4 kilometers. So I'm going to put a little I here for initial, because that was her starting position. And then the position of Sally final, at the end of the time that elapsed, was +5 kilometers, right? Because that's where she's standing now. Okay? So I in this class will always mean initial. That's where you're at the beginning of your time interval. And f, lowercase f, will usually mean final. And that means where you're at the end of your time interval, right? So in this instance, Sally started over here at -4, initial position of -4, and then she walks over to here to a position of 5. Cool? Now, another thing that we'll then be interested in is what's called displacement. All right? The symbol for displacement, let me clear up my ink here. So the symbol for displacement is a triangle in the letter x. So those of you who've taken chemistry hopefully know that triangle is the Greek letter delta, and it means change in. Okay? And so the definition of displacement is change in position, change in x, delta x. Okay? It tells you how much the position changes by. Okay? So to calculate your displacement, you merely subtract your final position from your initial position. So in that example we just did a minute ago, Sally's final position was 5 kilometers minus, so right, because she ended up here. I don't know why I erased. So she ended up here after starting here. Okay, so let's see. So her final position was 5. Her initial position was -4. So 5 minus -4, that gives you 9 kilometers. That's her change in position. In English, what is it? In English, this is just measuring how far she went, right? She started here, and then she went 1, 2, 3, 4, 5, 6, 7, 8, 9 kilometers, right? And notice she went this way, which is why this is positive, and we'll come back to that in just a second. All right? So it says here, this next example will illustrate this, but it says that notice both position and displacement have direction associated with them. All right, so in the next slide here, we're going to do an example, and that'll really illustrate this idea a little bit more clearly. All right, so that's what displacement is. It's your change in position. It's in English, it basically, I have to say that in English. The displacement basically just measures how far you ended up from your starting point, okay? And it has direction attached with it. All right. Distance, on the other hand, down here at the bottom, we've got this definition of distance again. It's the total length of the path that an object follows during some time interval. Okay. So scribble down those two definitions, and then on the next slide, I've got some examples that'll help you see the distinction between those. And ultimately, to be honest, really, this is the only one that we're going to care about this year. The only reason I'm even talking about distance is just because I think it'll help you. I think you'll better understand displacement if you also know what distance is, just so you can see how they're different. Okay? So, all right, so here we've got this number line again, okay? So now what we're going to do is we're going to find the displacement and the distance that Roy undergoes if he walks from, and then I've given you some positions, right? So for number 1, Roy's going to start here at a position of -7, and then he's going to walk all the way over here to a position of 9. Okay, so we've already done an example like this. I am color coding here. Notice example, problem number 1 is in red, so I'm drawing in red. All right, so displacement is final position minus initial position. His final position is 9 kilometers. His initial position is -7 kilometers. Subtract, and you get 16 kilometers. All right, and that's telling you that he went 16 kilometers this way. All right, now, in this next example, Roy is going to walk from a position of 9 kilometers back to a position of 3 kilometers. All right, and I want you to see what happens. So I'm going to do the same thing again. My change in position is final position minus initial position. So let's see, his ending position is 3 kilometers minus his starting position here is 9 kilometers. Notice what happens. When I subtract now, I'm going to get -6 kilometers. All right, so a minute ago I made the comment that the direction is important. All right, this negative sign here is indicating direction. It's telling me that I'm moving in a direction that leads towards my negative position. All right, so, you know, in math class on a number line, left is negative, right is positive. Here my displacement is negative. That means my displacement was 6 kilometers to the left. Okay? All right, now, what if we did both? What if we wanted to find the displacement for the whole thing? So Roy is going to walk from a position of -7 to a position of 9, and then back to a position of 3. Let's find the displacement for the whole thing. All right, well, there are actually 2 ways to do it. So probably the most straightforward way to do it would be to do this. Remember, all displacement cares about is your change in position overall. Where did you start? Where did you end? So in this example, this is my initial position. This is my final position. So my displacement is final position. Oh, I guess I should write it out with symbols. So it's final position minus initial position. So my final position is 3 kilometers minus my initial position is -7 kilometers. Subtract and you get 10 kilometers, right? Okay. Now, the other way that you could, so this, honestly, this is probably the easiest way to do it. And basically what we just represented there, I'm doing this in green instead of black, is this. We started here and ended here, right? So we went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 kilometers, right? And notice it's positive, indicating that overall my progress was to the right, because Roy ended to the right of the starting point, okay? Now, if you wanted to, the other way you can do it is you can just add the individual displacements, right? The displacement for the first part was 16 kilometers. In other words, he went 16 kilometers forwards. Then he came 6 kilometers back for a net of 10 kilometers forward, right? 16 plus -6 gives you 10. All right, but ultimately I really think that this is probably going to be your best bet, is to just stick with that guy. All right, so displacement is change in position, all right? Again, in English, basically what it means is it's telling you how far your ending point is from your starting point, and then that sign, the positive or negative sign, tells you the direction that you ended up in. So positive displacement means you ended up in a positive direction from your starting point. Negative means negative. All right? So let's talk a little bit more about that. All right? So this chapter we're going to be focusing on one-dimensional motion. So all of our motion is going to occur along a flat number line or a vertical number line. All right? If you're traveling along a line, there are only 2 directions you can go, right? So for example, if I've got a horizontal number line, like the ones we've been doing, there are only 2 directions I can go. I can either go to the right or to the left, right? And just like in math class, to the right is positive, to the left is negative, okay? So if you're talking about a road that runs east and west, east is positive, west is negative. If you're talking about a hallway that runs to the right and runs to the left, right is positive, left is negative. Sometimes it'll even just be as simple as forwards versus backwards, okay? Very frequently problems won't say anything about the direction, and we'll just assume that the object is moving forwards, so the direction will be positive, okay? Now, if the number line runs vertically, then it's the same thing as you would do in math class. So up is positive, down is negative, up, down, or if you're talking compass directions, north is positive, south is negative, all right? Now, to be clear, please, please, please hear me say this. You can only use positive or negative signs to indicate direction if you're dealing with one-dimensional motion, okay? Because that's the only time there are only 2 choices, right? Positive or negative. Eventually, we're going to get to 2-dimensional motion, right? Like Roy kicks a soccer ball, so the soccer ball goes, right? So sometimes the soccer ball is going this way, sometimes it's going this way, sometimes it's going this way. So here, there's an infinite number of directions that the soccer ball could be traveling, so we can't just use positives and negatives. And we'll learn how to deal with that when we get there, okay? So right now, everything we're doing is linear motion, one-dimensional, which means 2 possibilities, okay? Positive or negative. All right? Okay, so let's run through some examples here. In doing so, I'm going to show you a little bit about how I want you to solve problems. All right? So here, it says Roy drove his car 300 miles straight west to Chicago in 5 hours. How fast was he going? So prior to this video, what you probably would have done is you would have said, oh, well, he goes 300 miles in 5 hours. Oh, so that means he's going 60 miles per hour, right? Cool. And here, you're assuming that his velocity is constant, right? So what we really just calculated here is average speed or average velocity, okay? And to be clear, really what you just did here was you rearranged distance equals rate times time, right? You rearranged it. Rate is distance over time, right? And as a result, we get an average rate at which he was traveling, okay? I don't know that he was traveling 60 miles an hour the whole time, though, right? Like he probably stopped you know, whatever, to buy a taco, because tacos are good if you've never had one. And so while he was in line at the taco hut, you know, his velocity certainly was not 60 miles an hour, hopefully. Okay? So that's an average. All right? So what I'd rather have you do is solve it this way. So from this point forward, basically, we're going to be using this equation. We're going to be talking about average velocity. All right? So to calculate average velocity, here's your equation. You take your displacement and divide it by the time. I kind of oscillate between using t and delta t. There's not a huge difference between those. So don't get too tangled up about that triangle there in front of the t. They basically mean the same thing. All right, so average velocity. It's a measure of your displacement per unit time. Average displacement per unit time. All right, but let's suppose you actually did drive at a constant velocity. Let's suppose you set the cruise control at 60 miles an hour the entire time you were driving to Chicago, and you went in a straight line somehow. Okay? Well, in that case, if the cruise control is always at 60 miles an hour, then your average is going to be 60 miles an hour, and at any given instant, your velocity is 60 miles an hour, which means that your constant velocity at any given instant is equal to your average velocity for the whole trip, right? So that's really the type of motion that we're focusing on this chapter. Problems where you've got a constant velocity, okay? And so what happens then in that case is, if that's true, if your velocity is in fact constant, then distance equals rate times time becomes displacement equals velocity times time, or velocity is displacement divided by time. Again, no significance to the triangle here. Honestly, I wish I hadn't put either of those triangles there. I don't usually use them. Okay? So, what I would have liked you to have done then on this previous problem, solving it using, you know, kind of new physics-y terminology and new physics concepts, here's what I want you to do. So when you get a problem, start by writing down what you know. Roy drove his car 300 miles straight west. Oh, that's telling me how far he ended up from his starting point. So his displacement was 300 miles. Oh, and he went west. West is to the left. I know that on a number line that's to the left, that's negative, right? And I know that the time here is 5 hours. All right? Now, what I should have done then was reworded this. How fast was he going? I should have either said, assuming his velocity is constant, how fast was he going? Or I should have said, find his average velocity. Okay? And so then we can find our velocity, displacement over time. Negative 300 miles is how far his displacement was. This took 5 hours. So he averaged 60 miles west per hour. Notice, just like displacement, our velocity includes direction with the same exact logic, right? We went west 60 miles each hour. Okay? So there's your answer. All right? So when you solve problems, I want to see this. I want to see you starting by writing out your given information, then give me an equation, then plug in your numbers, and then give me an answer. Okay? Every problem should start this way. There are a bunch of you who at the beginning of the year are going to be like, why do we have to write this all out? Why do I have to write this all out? So by the end of the year, you're going to have, oh shoot, I put it away, a giant list of like 100 equations. And the most common question I get is, I don't know which equation to start with. And I promise you that if you get in the process of starting with this, it will make your life easier. Every year, a month into the year, I have kids that go, I was really struggling, and then I started writing out my givens, and that made it way easier. So just start now. It will make your life easier. This is not me being like, do it my way. This is me having taught this for 20-something years and knowing that this makes students more successful. Okay? So there we go. All right, so we got a couple other examples here. So we already talked about all this stuff. I think I've hit everything on here. So remember, displacement is how far you end up from your starting point. Direction is included. Distance is how far you actually travel. Velocity is how fast you're going. Remember, there's direction included. A lot of books will give you a definition. They'll say that velocity is speed and direction. Okay? So in that last example, I was going 60 miles an hour west, so the velocity was negative 60 miles an hour. The speed is just 60 miles an hour, right, without the negative sign. So for this chapter, the direction is going to be the positive or negative, and then the speed is the number part, 60 miles per hour. Okay. All right, cool. I don't know that we need to say anything else there. All right, so let's chug through a couple more examples. So this last one, I think I already said this, so note that at any given instant, velocity is the same as speed, except it includes direction. So for linear motion, the direction can be expressed as a positive or negative. All right, let's talk units. So displacement is a measure of how far you've gone. So displacement can be measured using any unit of length. Okay, we will usually use meters, but occasionally we'll use miles. Notice M is meters, MI is miles. The only weird exception is in MPH. This M is miles, just because it's on street signs all over the place, and I think we just kind of know that, right? Okay, but in general, M is meters. All right, so M is meters, miles. We can use kilometers, we can use inches, we can use feet, we can use yards if you're into football. You can use centimeters or whatever, all right? Time, we will usually use seconds, but if you want, you can use hours or minutes, MIN for minutes, or days, or weeks. You can't use months, though, because not every month is the same length. All right? And then velocity, remember, tells us our displacement per unit time. So our units of velocity are going to be one of these, any one of those blue ones, per unit time. Okay? So units of velocity could be meters per second, meters per hour, meters per minute, meters per day, miles per second, miles per hour, miles per minute, blah, 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 right? Anything from the blue column or row per anything from the red. We will usually use meters per second as we move forward. All right? For these first couple of worksheets, I'm going to use all of them, but within a couple of worksheets, it's pretty much going to always be meters per second. All right? So, example 2, car travels south at 42 feet per second for 15 seconds. How far will it go? So, let's model how we solve it. So, start by writing out your givens. Let's see, 42 feet per second. Don't just write down the number, tell me what it is. Let's see, feet per second. It's telling me distance per time. Oh, so it's a rate. Oh, but we call that velocity. Oh, and I'm going south, so I need to make it negative. All right, and we're doing that for 15 seconds. That's an amount of time. How far will it go? Oh, I'm looking for displacement. So that's your first step. Then solve it. Look at your equation sheet, pick an equation. Displacement is velocity times time. Oh, so we're going, let's see, negative 42 feet per second for 15 seconds. Grab your calculator, multiply it out, and you get negative 630 meters. So my displacement here is negative 630 meters. How far did it go? I guess that's not really specific, whether it includes direction or not. So if you answered 630 here, that would be fine also, if you ignored the negative. Your displacement's negative 630 meters. How far you went, I guess, would just be 630 meters. Okay? All right. So this one's kind of the same thing. Here we're solving for time. I'm just showing you that you're going to be solving for different stuff. So how long would it take? How long would it take? Oh, we're looking for the amount of time that it's going to take for a car moving at 90 kilometers an hour. So that's a rate. So that's my velocity. It doesn't say anything about the direction. So let's just assume that we're going forwards and we'll make everything positive. And the question wants to know how long it's going to take us to go forward 720 kilometers. So that's my given. Here's my equation. Displacement is velocity times time. Let's see, I'm looking for time though, right? So let's multiply both sides by velocity, and you get this, right? Algebra, okay? And then plug in your numbers. So let's see, my displacement, we went forward 720 kilometers at a velocity of 90 kilometers per hour. Multiply, and you get 8. Let's see, kilometers cancel, and you're left with hours. You can use either H or HR for hours. All right, and I think this is our last example. All right, so remember, here's the point of this last example. We've now learned 2 equations for displacement. We've got the definition of displacement, and we've got sort of the cause of displacement, right? That you've got velocity for some amount of time, right? Okay, so let's go through this and write down what we know. Roy is at a position of negative 4 meters when he begins walking north. Oh, so that's telling me that his starting position is negative 4 meters, right? It's not telling me how far he went. It's telling me where he is at the beginning. All right? And then his velocity is 6 meters a second. It implies, well, he's going north, so it's positive. You don't have to put the positive sign. I often do it just to remind myself that I thought about it. So he's moving at 6 meters a second for 5 seconds. That's implying that for the entire 5 seconds, that's his velocity. So I'm going to make a little note here to myself that it's constant. And I know my time is 5 seconds. And the question wants to know what position he will reach. So we're looking for a final position. Okay? So a couple of ways of doing this. I'm going to basically break it up into 2 steps. So step 1, let's do this. I know my velocity and my time, so I can find my displacement. Displacement is velocity times time, right? So I'm going at 6 meters a second for 5 seconds. I'm going to go 30 meters, right? Oh, and now I can use this guy. Displacement is final position minus initial position. So add initial position, and you find that the final position is change in x plus xi, right? So let's see, our displacement was 30 meters. We began at a position of -4 meters. So you're going to get, what, 26 meters for a final position? Okay. So that is that. That's about as hard as they get. Okay, and I guess, I don't know, yeah, I'm going to leave it at that. I don't need to draw that. Okay, so tomorrow we're going to look at how to graph all of this, all right? So, there you go. Oof, I talked long.